We are looking at calculations involving solubility product, or calculations involving solubility of sparingly soluble salts. I'm going to be looking at a number of examples on this, and it is those examples that will make us understand this very interesting concept, and will mark the end of solubility equilibria. We have been looking at a number of concepts in solubility equilibrium of sparingly soluble salts, but this will mark the end of the whole subtopic in physical equilibrium. I'll begin with a question. I begin with a question which will lead us to other parts of the concept. The first question I'm going to look at says, the question says, the solubility of this should be the solubility product of zinc hydroxide is 4.5 times 10 power negative 17 moles cube dm negative 9 at 25 degrees Celsius. This is part A of the question. It says, part A says, write the expression for solubility product of zinc hydroxide. So what do you do for this kind of question? We are looking at part A says, write the expression for solubility product of zinc hydroxide. I'll be looking at a part of a question and then the answer to it. Now, this question requires an expression, but most of you, the moment they ask you an expression, you end up writing an equation. So don't write an equation the moment they ask an expression. If you don't know the expression, go aside and do some side work, whereby you will know that zinc hydroxide being sparingly soluble, the equilibrium of it will have us get zinc 2 ions and then hydroxide ions. There are 2 of them. So that means the expression for solubility product KSP is concentration of zinc ions multiplied by the molar concentration of hydroxide ions, but this one is squared. Are we together?
Yes, teacher.
So this is not part of your answer. This is an equation. And in paper 1, even in paper 2, we always attack the question by what they have asked us. This should be the answer to the expression that they want. Otherwise, in case they ask one equation, write the equation first, then you go to the expression. So that answers our part A of the question. What does part B require us to do? Part B says, determine the concentration in moles per liter determine the concentration in moles per liter of zinc ions and hydroxide ions in a saturated solution of zinc hydroxide at 25 degrees Celsius. That's our next question. It says, determine the concentration. Determine the concentration in moles per liter of zinc ions and hydroxide ions in a saturated solution of zinc hydroxide at 25 degrees Celsius. So how do you get the concentrations of these ions? Remember, in the question they gave us the solubility product. That's what is given to us in the question. So what are we supposed to do? What we are supposed to do is very simple. So what we are supposed to do here is a very simple approach. We are going to write expression for solubility product and then substitute the value of the solubility product so that we get the concentrations of these ions. How are we supposed to do that? We are supposed to do that by, remember, we have the solubility product expression, Ksp is equal to concentration of zinc ions multiplied by the concentration of the hydroxide ions, but this is squared. And this is equal to the value we are given in the question. They have given us that value as 4.5 times 10 power negative 17. Remember, in paper one, our space is limited. It's not always good to write this expression, then write again Ksp down here. That's why you're seeing me doing this. This is to orient you to the way you should try to arrange your work. Now, we don't know these concentrations, and there's no way you can get them if you have two unknowns. Remember, from this equation, zinc hydroxide plus aqueous is giving us zinc ions plus 2 hydroxide ions. Okay, so you let the solubility of zinc hydroxide be X moles per liter. That's how your work will become simpler, because you want these concentrations. So if you let that solubility be X moles per liter, let me hope your calculators are just near you. Then zinc hydroxide to zinc ions, mole ratio is equal to 1 to 1. This implies that, this symbol means this implies that concentration of zinc ions is equal to also X moles per liter. Are you getting me? You must put these units. Then also zinc hydroxide to hydroxide ion concentration. According to the equation, the mole ratio here is 1 to 2. This implies that the concentration of the hydroxide ions is equal to twice X moles per liter. What does this imply? This implies that our Ksp expression now becomes Ksp is equal to concentration of zinc ions is X multiplied by 2X squared, which is equal to 4X cubed, which is all equal to 4.5 times 10 power negative 17. Are we together?
Yes, teacher.
So x cubed here is equal to 4.5 times 10 power negative 17 divided by 4, meaning that x is equal to the cube root, or 4.5 times 10 power negative 17 over 4, the whole of this power third. Can you compute from your calculators and tell me the value of x?
2.24.
2.24
Exponent negative 10 negative 6.
exponent negative.
Negative 6.
Yes, that is it. That's our value of x. Now, if this is our value of x, you may put units, you may not, because you've already assigned it units here. X already has units here. So putting units here implies you're doing repetition. Now, if that is your value of x, the question was very clear. It wants concentration in moles per liter of zinc ions and hydroxide ions. So what is the concentrations? What's the concentration of zinc ions? The concentration of zinc ions is equal to x and is equal to that value we have just got. We are now answering the question, which is 2.24 exponent negative 6 moles per liter. Then the concentration of the hydroxide ions is equal to 2x, which is equal to 2 into 2.24 exponent negative 6. That is 4.48 10 power negative 6 moles per liter. So by that, we could have answered the question. Are we together?
Yes, teacher.
Another question, which is a question of thought, could be part C of the question. It says, state how solubility of zinc hydroxide would change if to its saturated solution, is added Roman 1 ammonia solution. Roman 2, if its saturated solution is added aqueous sodium hydroxide. Roman 3, aqueous zinc sulfate. Roman 4, aqueous sodium nitrate. The question is just telling you to state how solubility would change. Who can tell me how will solubility change if I add ammonia solution? Which factor is being investigated here?
Complex ion formation.
So how will solubility change here? Solubility increases according to our previous lessons, right? Complex ion formation increases solubility.
Yes,
The
teacher.
question is just telling us to state, not to explain. What happens when you add sodium hydroxide? Which factor is being investigated here? Which factor is being investigated by adding sodium hydroxide solution? Remember, this is zinc hydroxide.
Complex ion formation.
Are you sure this is complex ion formation? We're adding zinc hydroxide to we're adding sodium hydroxide to zinc hydroxide. This is a soluble salt, remember, and this is sparingly soluble. So this factor here is common ion effect. Are we together? And since it is common ion effect, solubility decreases according to our previous lessons. When you add zinc sulfate, you're still testing common ion effect. Also, solubility decreases. When you add sodium nitrate, it is a compound that is soluble but containing no similar ion. The nitrate ions will tend to react with zinc ions at equilibrium to form zinc nitrate, reducing the concentration of zinc ions. More zinc hydroxide dissolves. So here solubility will increase. Remember our previous factors. So since the question is telling us to state, we don't explain. I leave the explanations to you. You'll try in your free time to explain why each of these leads to the change we have seen in its solubility, as we saw in our previous lessons. Can I proceed?
Teacher,
Yes, please.
why don't we talk of complex ion formation with aqueous sodium hydroxide solution?
With sodium hydroxide, remember we are just adding aqueous. We're not adding excess of it. In case I added
Yes, teacher.
excess and no excess of it, then we'll talk about complex ion formation. So if I wanted complex ion formation, I would go ahead to say excess sodium hydroxide. Am I clear?
Yes, teacher.
All right. I want to see another question here about solubility product. If this is driven home, I want to see another question. And that question is question 2. Question 2 says, in that first example, we have been given solubility product and we are being asked to get solubility. In my second example, I'm going to say the solubility of calcium phosphate is 0.0011 grams per 100 grams of water at 25 degrees Celsius. Calculate what's happening. Calculate the solubility product. Calculate the solubility product of calcium phosphate at the same temperature. Calculate the solubility product of calcium phosphate at 25 degrees Celsius. So in this case, what do you have to do first? What you do first is to write equation for the reaction for solubility of calcium phosphate in water. So what will our equation be? This is calcium phosphate. Calcium has valence 2, and the phosphate radical has valence 3. The moment you write a wrong formula, your equation becomes wrong. So this one being sparingly soluble will give us 3 calcium ions and 3 phosphate ions. Sorry, this should be 2 phosphate ions. This formula is wrong. Calcium has valence 2, so there is a 2 here. and hence a 2 here. So 3 calcium ions and 2 phosphate ions. This implies that our solubility product expression can be got from this. So Ksp is equal to the concentrations of the calcium ions, molar concentration of calcium ions, power 3, multiplied by the molar concentration of the phosphate ions, 3 minus, this one is to power a2. So to get Ksp, we must have this and this, which we substitute here and get our Ksp our Ksp value. However, these are molar concentrations. The square brackets here imply molar concentrations, which we don't have according to the question, but we are given solubility in 100 grams. This means we must first of all convert this solubility to moles per liter. And that implies that somewhere we shall need RFM. And before we get RFM, let us first get the mass that will dissolve in 1,000. Because 1,000 grams, we shall be tending to a liter. And we have to convert the grams also of the water, the 1,000 grams, to cc's using density of water. So we shall say 100 grams of water dissolve 0.0011 grams of calcium phosphate. How about 1,000 grams? 1,000 grams of water dissolve 1,000 times 0.0011 over 100. So this gives me which value? Which value does it give me according to your calculators?
0.011.
Gives me 0.011 grams. Those are the grams in 1 liter. However, we have been using grams. So let us say density, volume of water is the mass, 1,000 grams, times the density, 1 gram per cubic centimeter. That gives me 1,000 centimeters cubed, such that this implies that 1,000 centimeters cubed of water dissolve the same value which you have told me, 0.011 grams of calcium phosphate. Now you get molar mass of calcium phosphate. Molar mass of calcium phosphate is equal to 3 times 40, that's for calcium, plus phosphorus is 2 times 31, oxygen is 4 times 2, that's 8 times 16. Which value do you get from that? Value do you get from that?
310.
310 grams. So this implies that moles of, actually I will not call it moles. I'll take it as molar concentration of calcium phosphate. Because these are grams in 1 liter. So that will be 0.011 over 310. Which answer do you get from that?
You get 3.55. 55.
Is it 55 or 855?
It is 548.
3.548.
Yes, times 10 exponent negative 5.
3.548.
548.
10 exponent
Negative 5.
negative 5. This is now capital M. Now, after having got that, you will get your answer finally. So we shall say concentration of calcium ion, according to the equation we have here, it will be 3 of that value, not so. Thrice that value, right?
Yes, teacher.
This will be 3 into concentration of calcium phosphate, which will be 3 times 3.548 exponent negative 5. This gives me answer here is 1.06 exponent negative 4 molar. Then concentration of phosphate ions will be, according to this equation, that will be twice the same value. Mole ratio here is 1 to 2. So that will be twice concentration of calcium phosphate, which will be 2 into 3.548 exponent negative 5. So that one will give me which value? 7.096 exponent negative 5 molar. So your Ksp will be, according to this expression here, the calcium ion concentration is cubed. So that will be 1.06 10 power negative 4 cubed into 7.096 exponent negative 5. This is power which value? I think this one is squared, right?
Yes, teacher.
When you compute that, it will give you 5.977 exponent negative 21. This is moles per liter cubed, and this is moles per liter squared. So which units did you get? It is mole cubed, mole squared, that is mole power 5, right? This is dm negative 3 power 3, that's negative 9. Negative 3, 2, that is power negative 6. Remember, with the multiplication, you add powers. Is that negative 15? So that is the unit for Ksp in that case. Let me hope everything is clear up to this point.
Yes, teacher.
Yes. From simpler to complex, I'm looking forward to seeing another example involving a sorbitol product, but in this case, I'm going to do an example that involves something like common ion effect. Okay. A question involving common ion effect. That question goes, it says, the solubility of lead 2 sulfate in water is 0.035 grams per cubic centimeter at 17 degrees Celsius. Calculate calculate its solubility in 0.02 molar lead to nitrate. Here I want your extra attention. Lead to nitrate solution at the same temperature but in grams per liter. So bit of lead 2 sulfate in water is that at 17 degrees Celsius. Calculate its solubility in that concentration of 0.02 molar lead to nitrate solution at the same temperature. What are we going to do in this case? Analyze the question first. You're given solubility of lead 2 sulfate in water, which is this. But in such calculations, don't deal with concentration in or solubility in grams per liter. We deal with it in moles per liter. This is to help us get what we call KSP after converting it to moles per liter. That KSP, we shall later use it to get the solubility of the same compound in lead to nitrate, where the whole concept that's being tested is common ion effect. So first of all, write the equation. Although I have not been told to write the equation, it will aid you in the calculation. So lead 2 sulfate, being sparingly soluble, will give us lead 2 ions and sulfate ions. Each of the ions has a valence of 2, so it makes our equation very simple. So from this, we can get the expression for KSP as concentration of lead 2 ions, concentration of sulfate ions. That's the expression. We don't have this, neither do we have this, but we have the solubility of lead 2 sulfate in grams per liter, which you can convert to moles per liter and be able to get the concentration of each of these ions. How shall we do that? We shall say molar mass of lead 2 sulfate is equal to 207, that is for lead, plus sulfur, sulfur is 32, plus oxygen, which is 16 times 4. When you add up this, you get your answer as molar mass of lead 2 sulfate is usually 303. I'm putting units here because I'm dealing with molar mass. I'm not dealing with RFM. So the units here will be grams. So what is our molar concentration of lead sulfate, which is the moles in 1 liter? That will be 0.035 over 303, which will give me 1.16 exponent -4 molar. That is its molar concentration. So according to the equation, the molar ratio here is 1:1. So that implies that the concentration of lead 2 ions is equal to the concentration of the sulfate ions, according to the molar ratio there, and is equal to the same value. Are we together?
Yes, teacher.
So this implies that our solubility product, KSP, is equal to 1.16 exponent -4. According to this, we are just squaring this value. Do you realize that? Because they are the same, eh? So this is squared, giving me which value? It gives me 1.33 exponent -8 moles squared. Units are very important here. EM -6. Remember, this is moles per liter being squared. So that's our answer for KSP with its units. That one is going now to be very important for us to get solubility of the same compound in presence of a common ion, which in this case is the lead to iron according to this. Can I proceed? Is everything clear up to this point? Can I go ahead?
Yes, teacher.
Okay. Now let's say we want the solubility. You let the solubility of lead 2 sulfate in 0. Which concentration was it? 0.02 molar lead 2 nitrate. Let the solubility of lead 2 sulfate in 0.02 molar lead 2 nitrate be Y moles per liter. That's what they want us to do. Rewrite the two equations to simplify your work. We are now dealing with a new concept. The first information was to help us, and always understand it like that, that the first information given is to help you get the solubility product, which you're going to use in the second case because it doesn't change. So I'm rewriting these equations. Lead 2 sulfate, plus AQ is giving me lead 2 ions plus sulfate ions. So since you have said its solubility in lead 2 nitrate is Y, this will be Y moles per liter, Y moles per liter, Y moles per liter. You get me when I do that? You get me when I do that, or you're lost? Let me hope you're still on track. This one is a strong electrolyte. For it ionizes in solution. We are dealing with common ion effect here to give us lead 2 ions and nitrate ions. Its concentration was given to us as, there is a 2 here. Its concentration was given to us as 0.02 molar. According to this will be 0.02 molar, and this will be 0.04 molar. Are we still at par?
Yes, teacher.
If you are still at par, the whole idea now is here. Look at the common ion. The two compounds are together, and the concentration of the lead 2 ion is going to change. How is it going to change? We are going to say that the concentration of the lead 2 ion is now Y plus 0.02 molar. That is in the presence of lead 2 nitrate. It is the other one from the, it adds up the concentration of the 2 ion from the sparingly soluble salt and the concentration of the lead 2 ion from the strong electrolyte or from the common ion compound that is being added. So if that's it, we take an assumption. We say, but Y is very small. Why is Y very small? Because this is a sparingly soluble compound. The concentration of the 2 ion gives us is very, very, very small. So if Y is very small, therefore we shall say that Y plus 0.02 is approximately the same as 0.02. In other words, this implies that almost all the lead 2 ions that are present are from the strong electrolyte. This one contributes less to the effective concentration of the lead 2 ions. Are we together?
Yes, teacher.
That's the assumption that is taken at that point. This implies that the concentration of the lead to ions we are going to use will be 0.02 molar. I want you to understand that assumption story is taken whenever we are dealing with common ion effect. The concentration of the sulfate ion, for it remains the same as it is here, as Y moles per liter. So we go back to our KSP expression, which we have. We remember we have the KSP now. It is 1.33 times 10 power negative 8. That's why we dealt with the first example. Substitute the lead ion concentration now, which is, what's the lead ion concentration? It is 0.02. Multiply it by the sulfate ion concentration, which is Y. Are you getting me, Muhammad?
Yes, teacher.
What is the value of Y now? Y will be, when you go back here, Y is 1.33 exponent negative 8. Divided by 0.02. Such that your Y is which value? 6.65 exponent negative 7 moles per liter. By the way, Y, which we have got, is the concentration of the sulfate ion. By the same time, when you come back here, it is the sorbate of lead to sulfate in lead to nitrate. Do you realize that?
Yes, teacher.
Now, this implies that we have got Y as the sorbate of lead to sulfate in lead to nitrate. However, our question told us that they want that solubility in 0.02 molar lead to nitrate solution in grams per liter. Always it is good to read the question and understand it. So how do we convert it to grams per liter? We multiply it by RFM. So you conclude by saying solubility of lead to nitrate, lead to sulfate in 0.02 molar lead to nitrate is 303, which is the molar mass of lead to sulfate, multiplied by 6.65 exponent negative 7, which gives me which answer? 2.01 exponent negative 4 grams per liter. Is everything fine?
Yes, teacher.
Okay. Now somebody can ask you to explain the difference in the solubility of lead to sulfate in water and in lead to nitrate using the answers above. So this value is 2.01 exponent negative 4. The other one was 0.03 grams per liter. Which one is higher? This one is the one in water. Obviously, you see that it is higher than the one in lead to nitrate. Do you realize that?
Yes, teacher.
Why is the sorbate of lead to sulfate in water higher than that in lead to nitrate? Somebody is asking you to explain the effect of common ion effect. I think everybody amongst you can be able to explain that, right?
Yes, sir.
Yeah, I hope you will try that in your free time.